Hi, in this video I'm going to do a walkthrough of the, this is an AQA A-level paper, paper 1 from 2018. Okay, so it's in organic and physical chemistry. It's a 2-hour paper, so I'm going to do it in, probably do it in 3 sections because it's otherwise it makes the video a bit too long. Right, so the first question is about the Born-Haber cycle. So there we've got one for Born-Haber cycle for magnesium oxide, and you've got to write in the missing symbols on the appropriate energy levels. Okay. So we're going to start off with, here we've got magnesium, the elements of the standard states. Here we're going down delta HF to form magnesium oxide. So the first step for this one here, what have we done? We have, that will be the atomization of oxygen, because look, we've gone from half O2 gas to O gas. In the next stage, what have we done? We've atomized the magnesium because we've gone from magnesium solid to magnesium gas. Right. So the next step is, right, well, what we've got to, we want to end up with a magnesium ion. So we've got to do an ionization energy. So the first one is going to be Mg. It's the first ionization, Mg plus, and that's going to be gaseous. Let's put the electron in, and oxygen is just the same. Nothing's happened to that. This next one is bigger. That's the second ionization energy. The second ionization energy is always going to be bigger than the first. That's going to go to Mg2 plus gas, and now we've got 2 electrons, and nothing happens to the oxygen. That's the oxygen gas. Right, now this one, the exothermic step, going down here, we are going to stick an extra electron. Remember, we've got to end up sticking 2 extra electrons into the oxygen there. The first one is the first electron affinity, so it can be Mg2 plus. Then you've got 1 electron now because we stuck 1 onto the oxygen. And that's going to be O minus. These are both gases. You've got to have the state symbols in, really important. And this one is this change here is the second electron affinity of oxygen, which is going to be endothermic. Put a negative electron on something which is already negative, so there's going to be repulsion there. Right, so that's the first part, 3 marks for that. And the next bit of the question is they ask you to work out the lattice enthalpy. Give you the data, so I'll just grab this data up here, make it smaller. Okay, so we've got to put our numbers onto the energy cycle, and it asks us to work out the lattice enthalpy of formation of magnesium oxide. So that is when you get 1 mole of gaseous ions, and you are going to form, and they're going to form 1 mole of ionic lattice. So that yellow arrow there, that is the lattice enthalpy of formation. That's what we've got to find out, that yellow arrow. So let's go about putting the right numbers in then. Okay, so let's look at this first arrow here, this one going down. Right, that is elements in the standard state forming that, so that's going to be delta HF for magnesium oxide, which is, we give us a value there, enthalpy of formation is minus 602. The first one is the atomization of oxygen. Now we're forming 1 mole of oxygen gas, so where are we? Atomization of oxygen. Now it doesn't give us that, it gives us bond dissociation. Now we've got to be careful there, because bond dissociation is when we get one mole of O2 and we break the bond that we've got there, and we form 2 moles of O gas. However, we are only forming 1 mole of O gas here, so we've got to halve this number. Okay, so we're going to be careful there. So it's half of 496, which is 248. So that's a pretty, a lot of people are going to make mistakes there. So that's going to be plus 248 there. All right. Now the next thing we're doing is we are atomizing the magnesium. That's just 1 mole of magnesium. That's fairly straightforward. So that's 150 for that one. And the first ionization energy of magnesium, that is going to be 736 plus endothermic. The second ionized energy is quite a lot bigger, it's 1450. Right, then we've got this, the first electron affinity of oxygen, which is exothermic, sorry, and that's minus 142. So put that in there, minus 142. And the second electron affinity is endothermic, so it's going to be a plus number, that's plus 7, what is it, plus 884. Now we've got to work out our lattice enthalpy. Now if you look in the mark scheme, you'll see like a massive string of numbers. Like you'll see like, 736 minus 480 plus 200 and so on, blah, blah, blah. Now you're very likely to make mistakes if you do it that way, how it's shown in the mark scheme. You do a diagram for a reason, and that's to help you. So what we've got to do is, let's first of all, we've got to work out how high is that purple increase there. So all we're going to do is add up the numbers. And we ignore the fact that that's a negative sign there. You're using a diagram, you can see, you just want to find out how high that is. If you want to be really picky about it, you can think, well, why do we reverse the sign? It's because we're going against the arrow, but don't worry about the arrows. So if you add all that up together, you get 3,186, okay? So that's 3,186, that purple number there. 3,186. Now, we want to know what this yellow number is. So what we've got to do, well, you can see we've got 3,186, and we've got to add that number to it as well. That's going up. So plus 884. But we went down this little bit here. So I'm going to take away that bit, minus 142. So do all that, and you get 3,928, okay? Okay, now, so that number is 3,928, and we have to think, what sign is it? Okay, now it's asking us for the lattice enthalpy of formation, so the arrow is going to be going down. Whenever you go down, that is a negative sign, because it's exothermic. So the answer, the lattice enthalpy, is equal to minus 3,928 kilojoules per mole, which is a very big, strong lattice enthalpy. Sodium chloride is, if you remember, about 780. This one is much bigger because you've got a double positive charge on the magnesium ion and on the oxygen ion, and also those ions are both smaller than the sodium chloride. So there we've got, that's the answer there. So we've done that question. Now let's move on to the next bit. Okay, with question 2. So this is about equilibrium, Kp. So we've got our nitrogen and hydrogen forming ammonia. Now this is really important for this question. It tells us that the nitrogen and the hydrogen are added in a 1:3 mole ratio. And if you look, that's the right ratio that they're going to react in. All right. And because they react in that ratio, they're going to be in a 1:3 mole ratio before, because that's what it says to start off with, but also after they've reacted, they're still going to be in that ratio, because every time 1 mole of nitrogen reacts, 3 moles of hydrogen react. Okay, so it says when equilibrium was reached, the total pressure in the flask was 150 kilopascals, and the mole fraction of the NH3 was 0.8. Calculate the partial pressure of each gas. Right, so let's find out the mole fraction. I usually use that symbol for mole fraction, a lambda. Okay, so the mole fraction of NH3, they tell us, is 0.8. So we know that the mole fraction of N2 plus the mole fraction of H2 has got to be equal to 1 minus 0.8. In other words, it's got to be 0.2. Okay, what else do we know? We know that these gases have a molar ratio of 1:3. Okay, so you've got 3 times as much nitrogen as hydrogen. Let's say we've got X moles of nitrogen. For X moles of nitrogen, we must have 3X moles of hydrogen. And the total mole fraction is 0.2. So that means the mole fraction of nitrogen has got to be a quarter of 0.2. So the mole fraction of nitrogen is going to be 0.2 divided by 4, which is 0.05. And the mole fraction of hydrogen is going to be 3 times that. So that's going to be 0.15. So we've now got our mole fractions of each of the things. Right, now how do we, from mole fraction, how do we go to working out partial pressures? Okay, so partial pressure is equal to, different color, partial pressure of a gas, let's say N2, is going to be equal to the mole fraction of N2 multiplied by the total pressure. So for N2, the partial pressure, or the mole fraction of N2 is 0.05, multiplied by the total pressure, which is 150. So that is going to give us 7.5. Okay, and this was in kilopascals. That's 7.5 kilopascals. The partial pressure of the hydrogen, well, again, that's going to be a mole fraction multiplied by the total pressure. So that's 0.15 times 150. Which is equal to 22.5 kilopascals. So, and then finally for the ammonia, the mole fraction of the partial pressure of ammonia is equal to the mole fraction of ammonia multiplied by the total pressure, that is 0.8 multiplied by 150, which is equal to 120 kilopascals. So that's our answers there for 3 marks. Calculate, in 3 marks it said calculate the mole fraction of each gas. That for the nitrogen, that for the hydrogen, and that for the ammonia. Okay, so now as what it says now is they want us to give an expression for the equilibrium constant for this reaction. So just to remind ourselves, the reaction was N2 plus 3H2 goes to 2NH3. Okay, so Kp is going to be the partial pressure of the products, NH3, and we're going to square that. And then we divided by the partial pressure of the N2, multiplied by the partial pressure of H2, and that's got to be cubed because you've got a 3 over there. Okay, now it will also ask us in a minute to work out the units of that, so I'm going to do that now rather than ask us if it will ask us later. So what we got on the top, we've got partial pressure of NH3, that's in kilopascals. So we've got kilopascals, and that's going to be squared, divided by kilopascals, that's for the nitrogen, and then we're going to have kilopascals cubed for the hydrogen. So simplify that, we get kilopascals squared over kilopascals to the 4. Simplify that, you get 1 over kilopascals squared. Put it onto the top line, you get kilopascals to the -2. Very straightforward. Okay, now they always do this, don't they? They always say in a, I'm going to grab this expression here actually, because we're going to need it in a minute. Okay. Now in different mixtures, so in case you couldn't work out the partial pressures, they don't want to stop you moving on with the question. Put that there so we can remind ourselves. They give you the partial pressures of all those, and you've got to put in the numbers. So you've got to put them into the expression and give the units kPa. Well, if you put the numbers in there, so you want, it's just a matter of putting the numbers into your calculator correctly, which is sometimes easier said than done. And I often make mistakes doing it, so be really careful. But if you put those numbers in, you will get an answer of, so let's see, ammonia, that's 1.1 times 10 to the 3 squared, divided by the partial pressure of nitrogen, 1.2 times 10 to the 2, and then the partial pressure of hydrogen, 1.5 times 10 to the 2, and that's got to be cubed. Put all those numbers in, you get 2.99 times 10 to the minus 3, and as we said earlier, you can round that up to 3.00. The unit's going to be kilopascals to the minus 2. Okay, so there's that question on Kp. Right, now the enthalpy change, okay, so let's just ask us about what's going to happen. So I'm just going to grab the equation again here. Writing it out again. Okay, so it says here 2.4. It says that the enthalpy change of the reaction is minus 92. So that means it's exothermic in this direction, in the forward direction, minus 92. Exo, all right? State the effect of an increase in temperature in the value of Kp. Right, so, let's just look at our Kp expression again, which I just punch there, move that down. Right. Now, Le Chatelier tells us, okay, if this is exothermic, tells us if we increase the temperature, it's going to try and undo that, tries to undo the change by moving in the endo direction, i.e. it's going to move backwards. Right, so that means we are going to have, it moves backwards, we're going to have less of this, so the partial pressure of that is going to drop. We're going to have more nitrogen and we're going to have more hydrogen. These two in the bottom are going to increase. So that means the value of Kp, top decreases, the bottom increases, is going to get smaller. When you change the temperature, Kp gets smaller. And just it's worth mentioning here, the trick question, sometimes they say, what would happen if you to the Kp if you increase the pressure? Kp, the value of Kp is not affected by changes in pressure. The position of equilibrium is changed by the pressure, yeah? So that equilibrium, you increase the pressure, there's more gas moles on the left than the right, so it will go forward. You'll get more ammonia, but that will not change the value of Kp. It may seem odd, but it doesn't. It changes the position, but it doesn't change the value of Kp. Right, now this question here is about entropy changes, delta H and delta G gives free energy change. Okay, so it says calculate the entropy change for the reaction between ammonia and oxygen. So what we've got to do is the entropy changes, we've got to, the change in entropy, delta S is going to be equal to the sum of the entropies of the reactants minus the sum of the entropies of the products. So if we just look at this equation here, we're going to have to do, well, for the products, we're doing blue. Well then, we're going to have 4 times 211 for the nitrogen oxides. And you're going to have 6 moles of water, so 6 moles of gaseous water 189. So you add that up, and you subtract from that, so let's do this in green, the reactants. So you're going to have 4 times the ammonia value, which is 193, plus 5 times the value for O2, which is 205. So do the blue minus the green numbers, and if you do that, you should get a value of delta S is equal to plus 981 joules per mole per Kelvin, or equation. Okay, so you can see this is there's even an increase in entropy, and that's probably common sense check. That's probably understandable, because if you look on the left hand side, we have got 9 moles of gas on the left, but on the right hand side we've actually got 10 moles. So we've increased the number of moles of gases, so yeah, you would expect delta S to be a positive value. Okay, so we've done that. I think we're going to need that value later for the next bit. So, and we also need delta H. So I'm going to write delta H down there. They tell us it's an exothermic reaction, minus 905 kilojoules per mole. Now notice that's really important there. Later on, the delta H value is in kilojoules, whereas this one is just in joules. So we have to convert the delta S units a bit later on. Anyway, we'll talk about that in a minute. Right, so I'll just grab that. Right, and now the next part. Calculate a value of the delta G that gives free energy change. Okay. All right, so let's put this data we need here. At 600 degrees C. Now the equation for delta G is, of course, delta G is equal to delta H minus T delta S, and we do have to convert our delta S into kilojoules there. Okay. Otherwise we'll get a completely wrong answer. Delta G and delta H both measured in kilojoules, and we have to convert our temperature into Kelvin. So 600 degrees C is equal to 273, so that's 873 Kelvin. Alright, so let's put the numbers in there. Delta G is going to be negative, and so that means the reaction is definitely going to be feasible. Delta G is equal to delta H is minus 905 minus right, we want 873 multiplied by, now we need to convert that into kilojoules, so that's 0.981. Do that, we get a value for delta G is equal to minus 1,761 kilojoules per mole. Very negative, so it's definitely going to be a feasible. It's going to be feasible reaction at that temperature. Okay. Now, this next question, it says, look, the reaction is carried out at a higher temperature. What is that going to do to delta G for this reaction? Well, let's see. If this T gets bigger, that means all of that number is going to get bigger, and it's a minus number. So that means overall, delta G is going to become more negative. So you can see, as you increase the temperature, it becomes even more favorable. Delta G becomes even more negative. Okay. Right, question now about platinum. Well, platinum is a heterogeneous catalyst in that reaction. Okay, and it says platinum acts as a heterogeneous catalyst in the reaction between ammonia and oxygen, provides an alternative reaction route with lower activation energy, described at different stages. This is a fairly standard question, and they only want it in quite superficial. It doesn't really tell you much about the chemistry of it, but what you need to say is that the reactants are absorbed onto the surface of the catalyst, the platinum catalyst. Right? The reaction occurs, and then we say the products desorb. From the catalyst. Okay, so pretty when the reactants adsorb to the surface of the platinum, some of the electrons occupy the vacant d orbitals in the platinum. That weakens the bonds. That's how it actually works. You don't need to say any of that. You just need to say adsorbed, reaction occurs, and then desorb. 3 marks. Okay. Right. is an oxidation numbers one then. So the oxidation number of change in oxidation number of nitrogen when ammonia is oxidized to NO. So don't forget that the sum of the oxidation numbers is equal to the charge on the species. Okay, and we hydrogen is always +1. Except in metal hydrides. Okay, so it's +1. Oxygen is always, of course, -2, except in peroxides. So, right, what's the oxidation number in ammonia? Then is going to be, so we're going to have to equal, the charge on ammonia is 0. Nitrogen we don't know. Each hydrogen is 1, so that's +3. So that means N is equal to -3 there. And then the NO, charge on the species again is 0. Nitrogen we don't know. Oxygen is always -2. The algebra there, N is equal to +2. Okay, so it's +2 there. Okay, now it says here, when ammonia reacts with oxygen, nitrous oxide, okay, it can be produced instead of NO. Give a reaction to that equation. Okay, so we're going to have NH3, and we're going to react it with oxygen to give us N2O, and the hydrogens are going to combine with the oxygen to form water. So we obviously need to double the ammonia to balance for the nitrogens there. That means we've got 6 hydrogens, that means we're going to form 3 waters. Now we've got 3 oxygens in the water, 1 in the N2Os, 4 oxygen atoms, so that means we need a 2 in front of the O2. That would be the equation there. Okay, right, next question. All right, this is about the S block, okay? So, give the full electron configuration, that tiny bit bigger, for the electronic configuration of the calcium ion. Well, let's see where calcium is in the periodic table there. It's here. All right, so we are going to fill up, right, 1s is full up, so it's going to be 1s2. 2s is full up, there's 2s. Then we fill up 2p, all of those ones there, 2p6. Then we fill up 3s. Then we fill up all of 3p, so that's 3p6. Then we fill up 2 in 4s. 4s1 will be potassium, 4s2 for calcium. Okay, explain why the second ionization of calcium is lower than that for potassium. Well, as I said, for potassium then, it is calcium. Potassium would be the same, but it would be 4s1. So with potassium, the second ionization energy, we're removing an electron, not from 4s, it's gone, you're moving it from 3p. You're removing it from 3p. So that means then that with calcium, right, the electron is coming from the second ionization energy. First one comes from 4s, and the second one comes from 4s. It's coming from 4s. So with potassium, you're removing it from a new quantum shell. New quantum shell, closer to the nucleus, less shielding, I'd probably say, and so it's going to be much higher in potassium. Right, for 2 marks, I think you need to state the fact that one's coming from the quantum shell 3, that's coming from quantum shell 2, and then for the second mark, you do need to mention the shielding. The shielding is lower, and it's probably also a good idea to mention that it is also closer to the nucleus. I'd mention all of that. Just it's only 2 marks there, but sometimes they might actually give 3 marks for that question. Okay. Okay, question 4.3. Identify the S block metal that has the highest first ionization energy. Right, now here is the S block. Here, you've got the group 1 here, and you've got the group 2. In general, group 2, so for example, beryllium has always got a higher first ionization energy than lithium because they're both coming from 2s, but beryllium has got a higher nuclear charge. So it's always going to be group 2 is higher. And also don't forget, as you go down, it's going to get lower because you increase distance from the nucleus and increase shielding. So the answer here is beryllium is going to have the highest first ionization energy of all the group 1 the S block elements. Right, the formula of the hydroxide, that is the least soluble. Now you remember your trend in hydroxide solubilities for group 2. Group 1 hydroxides are all soluble. With group 2, as you go down, they become more soluble. Okay, but it tells us to ignore beryllium. So we're just talking about magnesium. So magnesium would be magnesium hydroxide, and of course the formula is going to be MgOH twice, because magnesium is a 2+ ion in group 2 of the periodic table. Right, next part of this question then. Okay, so it says here you're going to react barium chloride with sodium sulfate solution. Okay, now what's going to happen there is barium chloride contains Ba 2+ ions, and sodium sulfate contains SO4 2- ions. The chloride ions in the barium sulfate, they're not going to do anything. The sodium ions in the sodium sulfate, they're spectator ions also. But of course, barium sulfate is incredibly insoluble, so that's going to form a precipitate. So that is the ionic equation. I'll put state symbols in there. That goes in there. Okay, so they react in a 1-to-1 ratio. And it says, show by calculation, this bit here, which reagent is in excess. Okay, so we can see they do react in a 1-to-1 ratio, the barium ions and the sulfate ions. Okay, so let's work out the moles of barium ions. Well, 1 mole of barium chloride contains 1 mole of barium ions. So let's just work out the moles of barium chloride. So that's going to be concentration multiplied by the volume. Concentration is 0.25 multiplied by 6/1000 gives you that's going to give you 1.5 times 10 to the minus 3 moles of barium ions. Let's do the same for the sulfate ions now, moles of sulfate. And again, it's quite easy because 1 mole of sodium sulfate contains 1 mole of sulfate ions. So that's going to be concentration times volume. So the concentration of the sulfate is 0.15 of the sodium sulfate, and the volume is 8 centimeters cubed. That's 8/1000, and that is equal to 1.2 times 10 to the minus 3. Sorry. So you can see that this is the bigger number. So the barium chloride is in excess. Right, the next bit of this question, then I think it says how much of the sodium sulfate you need to add in order that it is, okay. Yeah. So calculate the total volume of the other reagent. In other words, this is the sodium sulfate we should use in order to make sure that it all reacts. If the filtrate only contains 1 solute, that means there's no there are no soluble barium ions, there are no soluble sulfate ions. You've only got sodium chloride ions. So you've got to make sure 1-to-1 ratio they're reacting. So we need to add more sodium sulfate. We need to add more of that. How much more do we need to add? Well, we know that the moles, the volume you're going to need is going to be equal to the moles divided by the concentration. Now the number of moles we need is this, the same as the barium, 1.5 times 10 to the minus 3, and the concentration is of the barium of the sodium sulfate solution was 0.15. So that's going to be equal to 0.01 dm cubed. So that's equal to 10 centimeters cubed. That's the answer there. Okay, so now this is not really anything to do with the S block elements anymore, even though strontium's in the S block. This is a working out relative atomic mass. Okay, right. Let's just do this first bit first. Why do these three isotopes of strontium? Why do they all have identical chemical properties? It's always 1 mark for that in the mark scheme, and you can't say the same number of electrons. You've got to be a bit more precise. You've got to say they've got the same electronic configuration. That's all you need to say. That will give you 1 mark. The other 3 marks is for the calculation, so let's do that. Okay, so calculate the percentage abundance of the 88 isotope in this sample. Right, now instead of using percentage abundances, I am going to here, first of all, use percentage, so e.g. you have 80%. It's easier if you write that as 0.8. It makes the calculations a bit easier. Right, now it says here, the abundance of these two is 1 to 1. Okay, so let's say the abundance, not in percentage but as a fraction, as a decimal, of 86 and so also 87 is, let's say, equal to x. So therefore the abundance of 87 is also equal to x. So what's the abundance of the 88? Well, we know all the abundances have got to add up to 1, so it's got to be 1 minus x for that one, minus another x, is equal to 1 minus 2x. Then we've got to just put them into the, so we know that for the relative atomic mass is going to be equal to the abundance of the 86 multiplied by, of the 86 strontium multiplied by its atomic mass, which is 86, plus the abundance of the 87 multiplied by its atomic mass is 87, plus the abundance of the 88 multiplied by 88. Okay, so let's put that, all those numbers in. Now they tell us that the AR is 87.7 there. So we're going to have 86x plus 87x plus 88 multiplied by 1 minus 2x. So we can see in that equation we know everything except x. So if we just simplify that out a little bit, we get that 87.7 is equal to 88 minus 3x. So that means that 3x is equal to 0.3. So x is equal to 0.1. X is the abundance of 86 and also of 87. So that's equal to 10% each. 10% for that one, 10% for that one. So that means the strontium left over is going to be 100 minus 10 minus another 10. It's going to be 80%. To 2 significant figures, or to 3 significant figures, 80 point. Okay, a quick common sense check would tell you that's probably the right answer. It is the right answer, but because look, they tell you the atomic the average value is 87.7. So it's going to be obviously got to be mostly 88 and smaller amounts of the 86 and 87, which it is there. Okay. Right. Time of flight mass spectrometry then, 4.7. Right, we can see identify the ion with the longest flight. Now, the ion with the longest flight is going to be the heaviest one. Why is that? It's because they all get the same kinetic energy. They all accelerated with the same kinetic energy, half mv squared. So that means if v is big, right down here, if m is big, if you've got a heavy one, if that's big, that means v squared has got to be small, so v's got to be small. So that means it's going to take longer to travel down the tube. That's the logic anyway. So the ion, don't forget here, so don't just write down 138. They won't give you the mark for that. You've got to write the ion, which is when it's lost one electron, so it's that single positive, 138 Ba plus. Okay, and then let's have a look at this. Okay, so it says here we have got this barium ion travels down the flight tube. It's given the kinetic energy there. They give us the equation for the kinetic energy here. They give us the time taken for it to reach the detector. And we've got to calculate the length of the flight tube. Okay, so let's write down the equation there. So we've got kinetic energy. I'll just write down E is equal to a half mv squared. Now, m is the mass of the ion in kilograms. All right, now we've got 137 barium, so mass of 1 mole is equal to 137 grams. So therefore the mass of 1 ion is going to be 137 over the Avogadro constant. Let's just write down L, and that's in grams. But we've got to convert it into kilograms, so the mass of 1 ion in kilograms is going to be that divided by 1,000, so that's 137 over 1,000 L. Right, now I'm going to put it into this equation, half mv squared. So we get E is equal to a half. Now m is 137 divided by 1,000 Avogadro constant, yeah, multiplied by v squared. Now you also need to note from your GCSE physics or A-level physics or whatever, that you need to know that velocity is equal to the distance, which is the length of the flight tube here, d, over the time, t taken. So let's just square that. So v squared is equal to d squared over t squared. And let's put that into that equation there. So I'm just going to rub that out. So I'm going to have d squared over t squared. What do we want to find out? It asks us to find out the length d. So let's rearrange that to get, but let's just do d squared first of all. And then we can do the square root afterwards. So rearrange that, we get d squared is equal to, right, 1,000 multiplied by the Avogadro constant, multiplied by the time of flight squared, multiplied by the kinetic energy, divided by half, and 137. Right, if you do that, you're going to get d squared is equal to 2.35. D will be in meters. Let's take the square root of that. So d is equal to the square root of 2.35, which is equal to 1.54 meters. And a quick common sense check, yeah, 1.54 meters would be a reasonable sort of size for a piece of apparatus. And if people do this wrong, they get like answers of like 10,000 kilometers long, which obviously the piece of apparatus is not going to be that long. So you've obviously gone wrong somewhere that you get an answer like that. Right. I think I'm going to continue with the rest of this question in the rest of this paper in the next video.